Today, we are really getting into something crucial: the conceptual foundation for evaluating time series models. It's so easy to get lost in just mountains of metrics and jargon. Our goal here is to cut through that noise, give you the theory you need to separate solid forecasting from just, well, fitting curves to past data. Get these core ideas right, and you really protect the integrity of your predictions.
Exactly. Integrity is the perfect word. We're defining what makes a forecast genuine. That means looking hard at the hidden assumptions, understanding different forecast types, especially when you bring in external data. And we absolutely need to adapt cross-validation correctly for time. Plus, figuring out what a good prediction actually looks like, both the point estimate and the uncertainty around it.
Okay, let's unpack this, starting with those unspoken rules. Before you even touch a model, what assumptions are hiding in the background?
Well, the first big one, and maybe the easiest one to break, is structural stability. We're fundamentally betting that the way things work, the relationships, the system dynamics you're modeling, will stay the same in the future as they were in the past.
Structural stability. Isn't that just a technical way of saying, hope the future looks like the past? I mean, maybe for something stable like utility use in a city, that holds. Where does it typically fall apart?
It fails spectacularly when the whole environment shifts. Think of major policy changes, new technologies disrupting a market, anything that fundamentally alters the rules of the game. You can't forecast electric car sales using assumptions baked from data when only gasoline cars existed, for example. Even if your inputs seem stable, if the link between them and your target changes, the model's flying blind.
Okay, beyond stability, what about the data itself? What are we assuming there?
We make assumptions about the process generating the data. Stationarity is a big one, meaning the basic statistical properties, like the average or the spread, don't systematically change over time. And if we're calculating prediction intervals, we usually assume something about the errors, like maybe they follow a bell curve, a Gaussian distribution, unless, of course, we use methods like bootstrapping, which don't rely on those distributional assumptions.
Right. And this brings us to what feels like a huge operational pitfall: data leakage.
Yeah.
Specifically about timing.
Oh, absolutely. This is critical. A truly honest forecast can only use information that was actually available when you made the prediction. If you're predicting tomorrow, you cannot peek at tomorrow's data. Not for training, not for validation. And this gets even trickier when you use external predictors in regression-type models.
External variables, right. So if my model uses, say, marketing spend to predict sales, how do I avoid cheating in the evaluation phase?
Good question. If you use external variables, they need to be leading indicators. Their value has to be known before the period you're forecasting. Or you have to forecast the predictor itself first. If you plug in the actual future marketing spend when testing your sales model, that's fundamentally flawed. You're poisoning your results.
Okay, here's where it gets really interesting, because this feels like the core divide in forecasting honesty: ex post versus ex ante. I have a feeling many people might unknowingly be relying on ex post results.
I think you're right, because ex post results often look much better on paper. See, an ex post forecast uses known actual future values of those external variables. So back to your example, predicting sales using ad spend. If you test your model using the actual ad spend from the test period, that's ex post, it basically tells you, well, if I had known exactly what the ad spend would be, my model would have been this accurate.
Which is not helpful for actual planning. It makes the model seem artificially good because it had information you wouldn't have had in reality.
Precisely. The real test, the honest measure, is the ex-ante forecast. That's truly out of sample. If your model needs next month's oil price, and you don't know it in advance, then you first have to forecast the oil price. Then you plug that forecast into your main model.
I see. And because that oil price forecast itself has some error, the error in your final sales forecast naturally goes up. It reflects the real uncertainty involved.
Exactly. That extra uncertainty is the cost of doing it right. It's the price of honesty. Operationally, this means for those external variables, you either need them to be true leading indicators, their lag is longer than your forecast horizon, or you need a two-stage process. First, forecast your inputs, maybe using simpler methods like exponential smoothing or ARIMA. Then feed those forecasted inputs into your main model.
This connects nicely to how uncertainty grows over time. Simple trend lines give simple fitted values. But many useful models are recursive, right? What does that imply?
Yeah. Recursive models like ARIMA or many state space models, they rely on their own previous forecast to predict further into the future. So to predict step 2, they often use the forecast they generated for step 1 as an input. It's feeding on estimated data, not known data.
Got it. So a small error in predicting Tuesday gets baked into the prediction for Wednesday and then Thursday.
Precisely. That error propagates and usually compounds. The model is relying on its own, potentially flawed view of the recent past. It means forecast uncertainty naturally increases, sometimes quite dramatically, the further out you predict. This isn't a flaw, it's the model being honest about its limitations. And it's also why standard cross-validation just doesn't work.
Okay, let's shift to evaluation then. Standard machine learning uses random shuffling for cross-validations. Why is that totally wrong for time series?
Because time isn't random, it has an order and dependencies. Shuffling time series data is it's like reading a book by shuffling the pages. You inevitably end up training your model on data from the future relative to the point you're trying to validate. Since models learn from patterns over time, letting future information influence past predictions is a major form of data leakage. Temporal order must be respected.
So we need special time series CV. But it's not just about respecting time, it's about mimicking deployment, right? What are the key things to match?
Yes, your CV setup should be like a dress rehearsal for the real world. 3 key things. First, evaluate at your target horizon, forecasting 12 months ahead. Don't just test on 1 day ahead accuracy, the errors behave differently. Second, match the refit frequency. How often will you actually update the model with new data? Weekly, monthly, never. Your CV needs to reflect that cadence. And third, circle back to predictor availability. Does your CV setup properly account for whether you need to forecast predictors? That whole ex-ante principle applies here too.
And often, to do this right, especially for model selection, we need 3 sets of data: training, testing, and a validation set.
That third piece, the final validation set, is often really important for getting an unbiased view. You use training and maybe a testing set or multiple CV folds to develop the model, tune parameters, maybe compare different model types. But the validation set, it's held completely separate. The model never sees it during development or selection. The errors on that set give you the best estimate of how the chosen model will perform on genuinely new, unseen data.
Makes sense. So what are the common CV schemes that follow these time-respecting rules?
The simplest is just a single holdout. Train on an initial chunk of time, test on the final chunk. Good if you deploy a model once and leave it. But much more common, especially if you refit often, is the expanding window or walk forward method.
Right. The expanding window sounds like it accumulates history. Start small, forecast, add the actual data, refit with the bigger window, forecast again.
Exactly. It mirrors learning from accumulating data. Now, if you think old data becomes irrelevant or even harmful, maybe because things change rapidly, then you might use a fixed window, also called a moving or rolling window. It keeps the training data length constant, just sliding forward in time.
Okay, that makes sense for adapting to more recent patterns. What if refitting the model is really expensive or time-consuming?
Then you might use periodic refits. Maybe the model takes hours to train, so you only fully refit it, say, once a month. But you still generate forecasts daily or weekly between those refits. Your CV needs to mimic that, only update the model parameters at those specific intervals.
All right, evaluation methods sorted. Now, metrics. Once we have these honest, out-of-sample errors, how do we measure performance? For point forecasts, we hear about MSE, PRMSE, PMAE, squared errors versus absolute errors. How do you choose?
It really boils down to how much you hate large errors. PMSE, prediction means square error, and it's square root, PRMSE. Square the errors before averaging. That means one really big miss gets penalized much, much more heavily than several small misses. So if a single large forecasting error would be disastrous for you, like massively understocking a critical item, PRMSE pushes the model to avoid those outliers at almost any cost.
So PRMSE is about avoiding the big screw-ups. PMAE, prediction mean absolute error, treats errors linearly.
Correct. PMAE just averages the absolute size of the errors. A 10-unit error is simply twice as bad as a 5-unit error. It might be better if you care more about overall consistency, and many small errors are more problematic than one rare large one. And, importantly, after picking your metric, remember the law of parsimony. If 2 models perform very similarly on your chosen metric, pick the simpler one. Fewer moving parts, less chance of overfitting.
Good point. But plain forecasts are only half the story, aren't they? We need to look at the prediction intervals, too. What makes a good interval?
Yeah. Intervals are crucial for decision-making under uncertainty. We want 2 things: honesty and precision, or coverage and width. Honesty is about empirical coverage. You calculate what percentage of your actual test data points fell inside the prediction intervals you generated. If you aimed for 95% intervals, did you get close to 95% coverage in practice? We want to minimize the gap between the nominal level, 95%, and the actual empirical coverage.
But we don't want too much coverage, right? Like 100% coverage probably means the interval is massive and useless.
Exactly. That's the precision part, measured by the average interval width. An interval stretching from -infinity to +infinity guarantees 100% coverage, but tells you nothing useful. So you want intervals that are as narrow as possible while still achieving something close to the desired nominal coverage. It's a trade-off. A well-calibrated interval is both honest about the uncertainty, good coverage, and reasonably precise, not excessively wide.
So what does this all mean? We've journeyed from fundamental assumptions to detailed metrics. What are the big conceptual takeaways for our listeners?
Okay, first and foremost, the ex-ante principle is non-negotiable for genuine forecasting evaluation. Reporting accuracy based on knowing future inputs, that's misleading, full stop. It's probably the single biggest trap.
Second takeaway. Your cross-validation choice isn't just academic, it's deeply operational. You must pick a scheme, expanding, fixed, periodic, that truly simulates how your model will be used and updated in the real world. That's key for trustworthy error estimates.
And third, evaluation needs balance. Look at point accuracy, maybe PRMSE if big errors hurt most, but also critically assess your interval quality. Are they hitting the right coverage level? Are they narrow enough to be useful?
That leads perfectly to a final thought. You might have a super complex model, maybe some deep learning thing, showing incredible point accuracy in an initial test. But if that test was actually ex post, using future information, that amazing score is an illusion.
Completely. The model that actually performs best in reality is often the one whose evaluation CV, metrics, ex-ante approach most faithfully mirrored its deployment conditions.
So the question to ponder is this: how many critical forecasts driving decisions right now might be based on validation that was closer to that unfair ex-post world than we realize? Something to think about when you look at your next forecast evaluation.